Hello again. Welcome back to the Baller Analyst, the official YouTube channel of indiaballer.com. This is the second part of the section on baller circulation. In the first part, I have talked about what is the need of the circulation, what is the objective of circulation, why it is needed. And we have seen that if circulation is not there in the boiler evaporator circuit in a subcritical system, then there is a possibility of the water wall tube puncture because of overheating, because the metals are remaining cool just due to the circulation, right? Now, in this particular video, in this particular part, we are going to discuss about how the circulation is created, right? And we are going to discuss about the difference between natural and forced circulation and once through circulation. What are the requirement when the forced circulation would be required? What are the advantages of forced circulation over natural circulation and vice versa, right? This part is going to be interesting, I'm telling you, because normally the way we think about circulation, uh, you might think that the idea is a little bit different. Okay, now a question is that what is the most important parameter of a boiler which is required to be controlled? Now that is definitely the thing which is known to every boiler engineer, and that is the boiler drum level, right? The boiler drum level is very important. In fact, there is a protection system in every boiler, I would say most of the boilers, where there is a low drum level annunciation would be there, alarm would be there, and low. We write it LO, not LOW. Low boiler drum trip. Now, have you ever thought why the trip has been given? Because everybody knows that if the drum level goes down, there is a chance of starvation in the water tube. But when we are having a low boiler water trip, boiler trip, right, because of the low drum level, is the drum empty? No, the drum is not empty. And if the drum is not empty, therefore the water walls are also not empty. And if the water walls are not empty, then where is the starvation, right? To understand that, we need to understand the circulation. Okay, the circulation, particularly in a subcritical boiler system. A subcritical boiler system may have a circulation called natural circulation. It can also have a forced circulation, and then there is another circulation which are very rarely seen in a subcritical system, but most often seen in a supercritical system, and that is the once through circulation. In the natural circulation in the evaporator circuit, there is no pump. It is due to the density difference as known by everybody. In a forced circulation or assisted circulation system, there is a circulating water pump in the evaporator circuit, and the once through system does not have any circuit. The feed pump pushes the water, it goes through the economizer, through the evaporator, somewhere in between it becomes steam and goes to the superheater and goes out, right? Now, the forced circulation is created by the pump, but how the natural circulation is created? Now we are going to take a closer look into this, how the circulation is created in the evaporator circuit, particularly in case of a natural circulation in a subcritical boiler system, right? So we are talking about natural circulation in a subcritical boiler system, which consists of a steam drum, a downcomer which is definitely located away from the furnace, outside the furnace, which does not get the heat of the combustion, right? And then there is the furnace water wall circuit, which are basically the riser tubes. So there is a steam drum, downcomer, the bottom ring header, and a number of riser tubes comprising creating the water wall section, the furnace section where the combustion is taking place. Now, if I just change this to a simple circuit with just a steam drum, downcomer, bottom ring header, and the riser, if I ask you how the circulation in natural circulation is being created, then answer is density difference. When I ask how the density difference is created, Some people answer that it is because the heat is received only in the riser tube and the downcomer tube is away from the furnace. That's why there is a temperature difference. Right? Wrong. There is no temperature difference. The whole evaporator circuit is at the same temperature, and that is the saturation temperature corresponding to the evaporator pressure. Because you see, from the steam drum, steam is coming out. And we know that when steam comes out means the water has to be at saturation temperature. From the steam drum, it comes to the downcomer, so there is no reason why the temperature is going to get down there. So the downcomer is also at saturation temperature. When it comes to the riser, it receives heat, but we know at saturation temperature, when it receives heat, the water becomes steam at the saturation temperature. There is no change in temperature. It is a constant temperature process. And this steam is going out of the drum, so the whole circuit is at saturation temperature. Now, how the density difference is created? The density difference is created because there is a density difference between steam and water. And the downcomer and the riser, the difference is the riser is having the steam bubble formed inside the water wall tubes, whereas the downcomer is away from the furnace where no steam bubbles are forming, so it is only water. So there is a mixture of steam and water in the risers, only water in the downcomer, and that creates the density difference between the downcomer and the riser, right? So if I create this circuit in a simple diagram with a steam drum, downcomer, riser, and let us say the water level in the drum is around h height from the bottom center line. Now this downcomer is having only water, so let us say the density is rho d in the downcomer, and the riser is having a mixture of steam and water, so the density will be different, it will be less. So let us say it is rho r. At the bottom center line of both the downcomer and riser, there will be head available, right? And we know that head is usually h rho g in case of any vertical water column, right? So it will be h rho d g below the downcomer and h rho g h rho r g below the riser. Okay, now which is more? Definitely the downcomer density is more, therefore h rho d g will be more. So we are having two columns with differential pressure that is going to create a delta P, right? This delta P will be h g, I take it common, rho d minus rho r. Rho d with only water density, rho r with a mixture of water and steam density, right? And that creates the delta P, that creates the circulation. So that is how the natural circulation is created. Now let us focus on this particular equation of delta P, which is basically the motive force behind the circulation. We can see one thing, that when the density difference between steam and water goes down, right, this rho d minus rho r, this part will go down, therefore the delta P will go down, right? Now when the pressure goes up in steam, in the last video also we talked about, when the pressure goes up, the density difference between steam and water comes down. It becomes zero at critical pressure, right? Higher the pressure, lesser is the density difference. At 120 ksc, it will be around 9.2 times, right? Even go farther, because a 500 megawatt or 600 megawatt boiler will have a pressure of around 185, 190 kg per centimeter square. At that high pressure, the density difference is hardly 5 to 6 times, not more than that. Now, if I go farther up, then at a particular density, the density difference will not be sufficient to create the circulation, right? And that is why normally at a pressure in excess of 160 bar, the density difference is taken to be not sufficient to create a natural circulation, right? But the fact is that at a pressure of above 191 bar, the natural circulation is not possible. Why I'm saying this? Because I have seen a couple of 500 megawatt unit boiler. One I can tell you at NTPC Farakka, there is an Ansaldo boiler, which is a 500 megawatt boiler, which is under natural circulation, right? And the pressure of that boiler is around 190 kSc. So till 191 bar natural circulation is still possible, but not usually practiced. Mostly above 160 bar pressure, that is, I'm talking about anything in excess of 250, 300 megawatt unit power plant boiler, where the drum pressure exceeds 160. Usually we see that the designer is going for a 4 circulation system, right? Now, even if I am having a lower pressure natural circulation system boiler, let us say 100 kSc, 120 kSc, right? That will be under natural circulation. Now, in this natural circulation, this rho d minus rho r, when it will be less? So naturally, you see, during the startup, when there is no steam in the risers, just before the startup, the density difference is actually 0, because both sides we are having water. And when the cold start, at the time of cold start, gradually the riser tubes will have steam after the heat is received by the riser tubes, right? And gradually the density difference will come. So the flow, the circulation will be very, very small during the cold start. That is one very important thing to remember. Any natural circulation boiler, during cold start, we should be very careful, because the circulation is not there. So naturally, if I ask you that whether the steam bubbles will form and leave the surface, answer is no, right? Initially, it is not going to leave the surface. So there is going to be departure from nucleate boiling at cold start, right? Okay, so departure from nucleate boiling will be there. But when we are having a cold start, at what temperature the steam forms in the initial stage? It doesn't go to suddenly to 160 kSc, right? So initially at the time of firing, the whole system is under atmospheric pressure. So I would say the first steam bubble is going to form at 100 degrees centigrade. Then gradually the steam formation will be there. Gradually the pressure will increase because the steam stop valve is closed and the temperature is going to rise. Now let us see a condition where the steam bubble is forming at 120 degrees centigrade in the initial cold startup condition, and there is a departure from nucleate boiling. That means the bubble is stuck to the surface. So naturally now it will become superheated, right? And by the time it is getting superheated, there are other steam bubbles are forming, and at one point of time that is going to create sufficient circulation and flow to drive this steam bubble up and away from the surface, right? So let us say by the time it becomes 300 degrees centigrade, the temperature becomes 300 degrees centigrade, it gets that circulation and leaves the surface. Will there be any problem? Because if the steam bubble is 300 degrees centigrade, the metal temperature is something more than 300 degrees centigrade, but not very high, because it will be around 10-15 degree more than that. And we know that carbon steel metallurgy up to 370 degree there is no problem, right? So no issue. But on other case, let us say the bubble is forming at 120 degree and getting stuck, departure from nucleate boiling, and by the time it gets the drive, the circulation sufficient enough to drive it away, right? It becomes 500 degrees centigrade and then it moves up. Will there be problem? The answer is yes, there will be problem, because if this steam bubble is 500 degree, means metal temperature is more than 500 degree and carbon steel cannot withstand that temperature. As a result, we are going to have failure issues, right? Overheating failure. Now what has gone wrong? Why by the time the temperature of the steam bubble is becoming 500 degree when it should be 300 degree? What mistake we are committing? So answer is definitely that during the cold start, if we are putting more heat load, faster heat load, if we are trying to ramp it up faster, right, that is going to lead to such kind of condition. If heat load is higher, at a higher heat flux we are giving the heat, right, then it can withstand, then it can take it away, then this condition will be faced, right? High heat flux during cold start, during fast ramp up condition. So overheating, I would say, will be a factor of two things. One would be when the circulation is inadequate, and the second is if the heat flux is very high. Even let us say if at the full load condition where the circulation is total, if there is a very high concentration of heat flux, for example, the flame, if it's a corner fired boiler, tangential corner fired boiler, the flame is supposed to be at the center as a flame ball, right? The fireball, which is supposed to be at the center, if shifts to one particular side of the wall, there the heat flux concentration will be higher. Even if the circulation is proper, then also we can have overheating condition, right? And circulation can get affected. That the first point I'd say, inadequate circulation. We have discussed this already at low load condition, at the time of cold start. But again, suppose there is an obstruction in the tube, then also circulation can get affected, right? So all this can happen. Now, let us say the high heat flux condition, if I want to avoid, I need to maintain steady loading during the ramp up, initial ramp up, cold uh, uh, startup condition. Now, how do I know whether the circulation is correct, whether this is the rate at which I can increase the heat load? How do I know all these things? Because we cannot see the circulation. We don't know if there is a departure from nucleate volume taking place in the system. We cannot measure the flow, right? In a natural circulation boiler, we don't have any flow measurement in the evaporator circuit, right? So answer is very simple. We need not to know. We need to just follow the OEM given boiler startup curve, because this has been created by the OEM and given to us with every boiler, that at what rate is basically time versus temperature curve, time in second, temperature in degrees centigrade. So at what temperature, at what time the what temperature should be attained. Usually the drum metal temperature and the fluid temperature in the drum is measured with this particular one, right? And drum metal temperature is measured everywhere. Now this startup curve, if you can maintain, then you need not have any problem, need not to worry about this overheating issues. But unfortunately, many a times it is not possible. Many a times, for example, I'm having a cogeneration system, right? There is a sudden requirement of process steam, and we need to ramp up our system fast, right? It was running under low load condition to maintain the plant steam load. Now suddenly the steam requirement has increased. Now I have to ramp up fast because it's the process requirement. Utility has to meet the process requirement. Now in that case, one may not be able to control this startup time. They may need to ramp up a little faster, right? I agree, it should not be done, but it is sometimes it is done practically. Now, what are the controllable parameters? In this case, this is the ramp up time is not controllable for us. So what are the controllable parameters during the cold start? So let us take a look again in the circuit and that particular equation of delta P. Now this delta P is getting affected by the delta rho, that is the density difference, but it is also a factor of this H, right? That means we are talking about the drum level. Now that tells you why the drum level is so very important. When the drum level goes down, the circulation becomes inadequate. So the low trip level is the level which has been decided on the basis of this understanding that below this drum level, the circulation will not be enough to sustain the reliability of the water wall tubes, right? Now, when I talk about cold start, there is a typical problem of drum level control, because you see, till 30% load is achieved, we do not have the three element control in the system, right? It is not in service because one of the element of three element is the steam flow, and steam flow measurement requires at least 30% flow through the tubes to have a proper measurement. So that means initially till 30% load is achieved, we are basically maintaining the drum level manually. Now at the time of cold start, another typical phenomena, I think all of you know about this, and that is called swelling characteristics of the boiler, right? Continuously the drum level tries to go up. And in power boiler system, one thing, if I tell you that if somebody asks you that in a power boiler, what we cannot do, go beyond the normal drum level or go below the normal drum level. You know that high drum level trip is also there, right? In every power boiler, there is a high boiler water trip, drum level trip. Now the answer is, in a power boiler, you cannot go above the high drum level. What is the normal drum level? You cannot go above that. You can go possibly below it at the cost of the boiler reliability. But if you go above, then there is a possibility of carryover, right? Water carryover with the steam, and if that water reaches the turbine, that is absolutely not acceptable. So what we do, because of this swelling characteristics, the drum level is continuously trying to go up, and it's very difficult to manually control the drum level at that time, and particularly during the cold start, every parameters are unstable, right? And a person has to look into all these things. So naturally, if somebody has been given many jobs along with that to control the drum level, then what he usually tries to do, so he set the manual drum level set point a little lower, so that even if he cannot control the drum level very finely, right, even if it goes up, it should not go up above the normal drum level. So the manual drum level set point we bring down at a lower set point, right? 50, 60, sometimes 100, sometimes 120 millimeter of water column. Now that is a very dangerous thing. You imagine, it's the cold start, there is no circulation. Management has asked to speed up the startup condition, right? Ramp it up fast. So huge amount of heat flux has been added. These two are not in your control. But the one which is in your control, that is the drum level, even that you are putting down at a lower set point just to avoid the condition where suppose some momentary mistake may lead to an exceeding that particular drum level, and then you would be in trouble, right? So that is a very critical parameter to monitor and maintain. Wherever I go, I always advise, and nowadays most of the good systems where good practices are there, a solitary person, right, has been exclusively given the job of maintaining the drum level, manual drum level at the time of cold start. It is very important to ensure the reliability of the system, right? So always remember this. Maintaining the drum level, particularly at the time of cold start, is very important when it is being done manually. Once it comes in three element system, then we don't have to worry about that. The swelling characteristics will be taken care of by the three element system, right? Okay, now if I summarize, let us say, what are the factors that may lead to the overheating condition, departure of nucleate boiling, and overheating condition of the water wall tubes? So the first thing is the very fast ramp up during cold start, that is number one. Second is low drum level, particularly during cold start, right? Third is, as I told you, if there is an obstruction in the tube, then that is also going to affect the flow. In fact, a boiler, after a long shutdown, immediately after the start, it has failed, right? There was a large bulging and fish mouth type opening in the water wall. Now this is a particular kind of an incident which you see everywhere, right? Quite frequently. Now whenever that happens, always understand that something has gone wrong during the shutdown, right? And this is a clear case of obstruction in the water wall. I have numerous such experience of cases, right, where this has happened. One way of avoiding it is that whenever you have a steam drum manual open, that is during annual overhauling mostly, whenever you have the steam drum manual open, then make a strict regulation, right, a rule that whoever enters the drum should have a inventory check. He takes 3-4 electrodes, he should come out with the tail of 4 electrodes, the remaining part of the 4 electrodes. He takes a lot of cotton waste. Now cotton waste is the most dangerous thing. So he takes a lot of cotton waste inside. He should come out with the same amount of cotton waste more or less when he comes outside. So this kind of an inventory check, you take one pen inside, you come out with one pen. Now this kind of inventory check helps in maintaining the water wall health in terms of the obstruction due to foreign object. Sometimes it happens accidentally, but accident happens. And of course there's a possibility when there is a scaling in the water wall tubes. If the water wall tubes have scale formation, then the heat will not be transferred to the water. The metal is going to be heated. Yeah, that will definitely cause overheating. But again, in most of the critical pressure boiler system, the water treatment is very good. The water quality, feed water quality is exceptionally good, and there is very little chance of scale formation, right? Whenever I get the chance of talking about the water chemistry part, I will explain why in a power boiler the scale formation is the least possible problem for us. But yeah, one thing is again might happen, and it's quite often it happens, and there is very high amount of heat flux at a particular wall, right? It can happen because of flame impingement. Flame impingement is nothing but the flame is coming very closer to the water wall. So in a front wall fired boiler, right, if the flame length is very long and it is almost touching the rear water wall tubes, then that would be called a flame impingement. In a corner fired boiler, if the central fireball is shifting to one particular side, which again is a very common issue, because most of the corner fired boilers, all 4 corners are very rarely properly balanced, right? As a result, the flame ball doesn't remain in the center, it shifts towards one side. So all these things will cause the overheating and departure from nuclear boiling and overheating failure in a water wall tubes, right? Okay, now let us talk about the force circulation. So I say that the force circulation will come when the density difference is very low, right? That means at a high pressure. So mostly at a pressure of around 160 bar and above, right, OEM goes for a force circulation. We call it assisted circulation also because it is assisted by a pump. Now let me tell you here, in various refineries and petrochemicals, you may find a waste heat recovery boiler which is at a very low pressure, let us say 4 to 6 bar pressure, right, just generating LP saturated steam by utilizing the waste heat. But you may see that there is a circulation pump in the circuit, whereas at 4-6 bar pressure the density difference is huge. So there should not be any need of force circulation. But there you are going to find that this evaporator might be where the evaporator tubes, the water wall tubes, are in horizontal configuration and at a very high elevation. So therefore the height, as you can see, the H is a very important factor. The height cannot be given there, because if you put the steam drum at a even higher altitude, even a higher height, that will become very impractical design, right? So in such cases, you might see that there is a forced circulation pump given in that circuit. Sometimes again, in some process boiler, for example, let us say I'm having a waste heat recovery boiler in a refinery at a some exothermic reaction is taking place in a reactor, right? So at this reactor, heat is being utilized to generate the steam through a waste heat recovery boiler. The steam pressure might be very low, 4, 5, 6 kgs per centimeter square, but you are going to find a, a circulating pump there, right? Again, the reason is not that it is at a very high elevation. It might be at a ground level, but the point is that see, during the cold start, right, when the reactor will be started, it's a process waste heat recovery boiler. So the startup is not because of the boiler. The startup is for the process. So when the reactor is started, the exothermic reaction might release the heat at a very fast rate. And we have seen that during cold start, if the ramp up is not controlled, right? Because normally, gradually, if the pressure increases, the steam load increases, then the circulation will be created. So in such cases, we have a forced circulation system. We first start the circulation pump and then we start the reactor, right? So this sort of things are basically can be seen in industry, and you may wonder what is the purpose of the circulation. I hope this particular discussion is going to give you all these answers. Now in a forced circulation system, there are certain advantages. See, since the circulation is taken care of by a pump, right? The head loss due to friction and all that, and due to which the natural circulation is mostly affected, is not a problem here, right? So the tube diameter becomes smaller in a forced circulation boiler, right? Tube diameter becomes smaller, the furnace height also becomes less, right? So that is advantage. Second advantage is, as again, we don't need to gradually ramp up, so we can have a very fast ramp up in our system. So cold start can be very fast ramp up, so less transit time for a cold start. That is another advantage, right? Some disadvantage, because the circulation is depending on the boiler circulating water pump, right? So we have to always have a very close check at the delta P across that, right? You can also have a flow measurement in such kind of a circulation system. So if there is a delta P problem and we do not get the circulation, then the boiler needs to be tripped, right? So there is an additional MFT, the master fuel trip, that will come in a forced circulation boiler on the basis of the differential pressure across the boiler circulating water pump. And in some cases there is a very sudden fluctuation of load, right? Suddenly the load requirement goes down, and suddenly the pressure goes down, particularly in case of a sliding pressure mode operation. I hope you know what is sliding pressure mode operation, right? So along with the load, the pressure also goes down. So the turbine valve remains almost fully open in such cases. So when the load goes down, the pressure also goes down. When the pressure goes down, there is a sudden pressure goes down, there is a possibility of the cavitation of the pump, right? So that is another issues that has to be very particularly monitored in case of a forced circulation pump. Once through circulation is mostly seen in subcritical system. That doesn't mean that subcritical system does not have once through. There are 88 bar, 100 bar pressure once through system available. I have seen one barge mounted once through boiler in Andhra Pradesh. Okay, so but yeah, supercritical systems are mostly commonly the one which you are going to see the once through, because when the pressure goes beyond the critical pressure, right, there is no transition between water and steam phase. the water gets heated, then there is no requirement of latent heat. Suddenly it becomes steam, and then it goes to the superheated condition, right? So in one-stroke system, the fit pump pushes the water, goes through the economizer, through the evaporator, suddenly becomes steam and start getting superheated and comes out at a superheated steam. So mostly the supercritical system will have this one-stroke system. Again, what are the advantages? Now, yeah, there are various advantages, because one thing is there is no need of drum level control and all that, right? You control the flow and control the whole system. Yes, it will make it also critical at the same time, right? But yes, you can have a faster load increase. The load variance can be very fast, right? So the faster response will be there to load change. Then you can have a very fast startup, same as forced circulation system. But again, there would be certain issues, right? One particular issue will be that the the sliding pressure is definitely adopted in a supercritical system. Nowadays, even all the 500 megawatt units are working at sliding pressure mode. Most of the 500 megawatt unit. But with the sliding pressure mode, the pressure also changes, right? Now, when the pressure changes, the steam, where it is forming and what part of the evaporator is forming, that might also shift, right? Now that is a problematic. The location of the water and steam phase change, right? They might change with the pressure. Now that is a big issue for a supercritical system, right? Okay. Now of course, the response of the boiler feed water, requirement of the boiler feed water chemistry is very easily understood, because in a natural circulation or forced circulation system where there is a drum, steam drum, whatever the water that is getting circulated, if it gets concentrated, right, we have a blow down possibility there. In this case, in a one-stroke system, whatever the water is coming is going out as steam. Therefore, the feed water quality has to be maintained as the steam quality that is required by the turbine. So definitely the water chemistry control becomes very, very critical in a supercritical system. Okay, so with that I have discussed about the natural circulation, the forced circulation, and the one-stroke circulation. Then one question remains. Sometimes I get this question that the circulation ratio. What is circulation ratio? How can we calculate the circulation ratio? What is the required circulation ratio for my boiler? All these questions I get from time to time. Okay, so what is circulation ratio? Circulation ratio is basically the ratio between the water that is going through the evaporator circuit, flowing through the evaporator circuit. Now let us say in an hour, certain amount of water is flowing through the evaporator circuit and certain amount of steam is being generated. So CR is the ratio between this mass of water flowing through the evaporator circuit to the steam generated at the same time. So if it is measured as tons per hour, the steam generation will be at tons per hour. Okay, this can vary in a natural circulation boiler from 4 to 22. In a forced circulation boiler, it will be a little less, around 1 to 2, sometimes 3. But again, the question is how to calculate the circulation ratio. Let me tell you, it is not our job. Not for those who are in operation and maintenance practice. It is not possible. Why? Because it is a designer's perspective, totally. The circulation ratio depends on various factors. The diameter of the tube, the height of the furnace water walls, right? Then the orientation of the tube, then the heat flux, how it is receiving the heat flux, and what rate it is receiving the heat flux. Not only that, what is the frictional loss in single phase in the downcomer, in two phase in the risers, what is the gravitational loss in the risers. So there are so many different factors are there. The pressure and temperature definitely, because the density will depend on that. So all these factors are required to calculate the circulation ratio. Now definitely this is not possible by an operation maintenance engineer. It is the designer's job, so let it be their job. The point is, why do I need to calculate the circulation ratio? I need to just understand one thing, that yes, circulation is required in my system, and I need to take care of those factors which are affecting the circulation. So as I have already discussed, in natural circulation boiler, the height of the drum level, right, the rate at which we are giving the heat, all these factors which are in our hand, possibly we can control and we should control. In a forced circulation system, having the circulating pump in good health, right, all those factors are controllable, so that is the area where we can control. So we don't need to know the circulation ratio. That is the basic point of fact. Okay, so here I am going to conclude my session. Before I conclude, let me tell you, I'm going to create a number of such videos in future and share with you, right? So if you want to get the intimation of such videos in future, I would suggest you can go to the YouTube channel, right? Just click on this subscribe button. So once you subscribe, then there will be this drop down button and the bell notification. Just click on this bell notification. There will be drop down menu coming. Just click on the all button and you are going to get all the notifications of any future video that I am going to share, right? So with that, I would say goodbye to you. Thank you and bye bye.